So hello and welcome to the York Universe podcast. It's the Astronomy and Astrophysics podcast written and presented by the students, faculty, alumni, and friends of York University. You will find us wherever podcasts are distributed. I'm Mary Helen Armour. I'm one of your hosts this evening, and I am joined by Julie Tomei. Tonight we are broadcasting live from the Allan I. Carswell Observatory on the Kiel campus, Ontario, Canada. York Universe broadcasts live every Monday at 9 p.m. local Toronto time, or currently 1 a.m. Tuesday Universal time. We also run in line with our online public viewing, or what we call our OPV, run by the observatory staff. And fortunately tonight, the sky seems to be reasonably clear. So the first few images you'll see coming up, if you are sort of following on YouTube, will be archival images. And as the sky gets dark enough, hopefully we'll be able to get some live images through the telescope. And these are running simultaneously with the YouTube chat. So if you are watching live on YouTube, please feel free to post any questions you might have in the YouTube chat, because we do have some of our wonderful student volunteers and work study students monitoring this, who will be able to answer your questions. Okay, to follow our live shows or learn more about us, if you're watching this video sort of after we have done it, you can visit yorku.ca/science/observatory and follow the link to our online public viewing on chat on YouTube. For any questions or comments about past shows, or if you have any suggestions for future topics, you can email us at observe@yorku.ca. You can also connect with us on Instagram at Yorku Observatory. We have a pixel fed at Allan I. Carswell Observatory, and a Facebook page at Allan I. Carswell Obs. Right? All of our programs are free, but if you'd like to donate, you can also visit our website, and we do have an option for donating. Again, we are monitoring the YouTube chat if you are with us live, and we'll be posting sort of content and stuff throughout the show. So hi, Julie. How are things where you are? Have you got clear skies overhead as well?
Hiya, I'm doing all right. Let's see. Let me peek out the window. And so. It
So
looks clear-ish.
clear-ish. So we're starting out with our usual This Week in Space and Astronomy History, and I think you have one dating back to the 1970s.
I do. We're going back to June 22nd, 1978 for the discovery of Charon or Charon. You pick the pronunciation. More on that in a second. So this is, of course, the largest moon of Pluto, and it was discovered by the U.S. Naval Observatory astronomer James Christie at the U.S. Naval Observatory in Flagstaff Station using a 1.55 meter telescope. For those who prefer their telescope measurements in inches, that is 61 inches. Christie had been examining highly magnified images on photographic plates that had been taken a couple months before, and noticed there was a slight elongation at times. And he started looking back at previous plates, dating all the way back through April 1965, and so was able to confirm that this was actually happening. There was some curiosity happening. And so more observations were taken. And it showed that the bulge was because there was a smaller body orbiting Pluto. And the periodicity matched Pluto's rotation period, indicating that these two are in a synchronous orbit. Pluto's mass, size, and other physical characteristics had to be recalculated after this discovery, because the initial math had been done assuming there was a single body there. The discovery was announced by the IAU, or the International Astronomical Union, on July 7th, 1978. Further bolstering the conclusions, Pluto and Charon entered a period of mutual eclipses and transits between 1985 and 1990, when the pair were visible edge on from the vantage point of Earth. And this only happens twice during Pluto's 248-year orbit. So some feel that this was fortuitous timing. Charon was given the temporary designated S/1978P1, which was according to a convention that had just recently been established. As for its formal name, Christie proposed Oz and then Charon as the name. His colleagues suggested Persephone. He had suggested Charon as a sciency sounding version of his wife Charlene's nickname Char. And only later found out that it was also the name of the ferryman of the underworld in Greek mythology, thus making it an appropriately related name as well. The name officially was adopted in 1985 and publicly announced January 3rd, 1986. And another fun coincidence is that there was an author, Edmund Hamilton, who wrote a book called Calling Captain Future in 1940. And he had invented, quote unquote, 3 moons for Pluto, which he had named Charon, Styx, and Cerberus. And the names Styx and Cerberus were used in 2013 for the two of the moons that were discovered in the run-up to the New Horizons flybys in 2015, with Cerberus in its Greek form, Karabos. Although I'm not clear if the book was related to those names being chosen. Either way, neat coincidence. As for pronunciation, the classical pronunciation is with a hard K sound. But as Christie named the moon in honor of his wife Charlene, he's always used a CH sound. And this is the convention that NASA and the New Horizons team used. You can choose whichever one you like. Don't fight over silly things. Pluto and Charon orbit each other every 6.387 days and are mutually tidally locked, meaning that always the same side of each is facing the other. With the barycenter of the system being outside of the radius of Pluto. So they really are orbiting each other. The individual masses of Pluto and Charon could only be estimated until the discovery of Pluto's other moons in 2005. And then that made the math easier. And Charon is about 12% of Pluto's mass. In 2005, Robin Canup did some simulations that suggested that, or to explore how Charon might have been formed through the hypothesis was through a collision 4.5 billion years ago, similar to what is believed to have formed Earth's moon. In this case, a large Kuiper Belt object moving at high velocity would have hit Pluto. The impactor would have been destroyed and stripped much of Pluto's outer mantle, and Charon would have coalesced from the debris. But this would have resulted in an icier Charon and a rockier Pluto than what has been observed. And just last year, there was a study led by Adine Denton, a NASA postdoctoral fellow at the University of Arizona. And this study suggests that there was a pair, they were already existing, they collided with each other. The collision was not strong enough to destroy either one. They stuck together and kind of like started spinning for a while until they separated and settled into their orbit. So, Charon, cool moon.
Yeah, and it just fascinates me when you think about it that, even in the 1970s, you were still finding fairly large objects, and we continue to this day, right? I mean, a lot of these very far out dwarf planets, we're still discovering them. I mean, technically, Pluto and Charon are more of a binary planet system than a planet and its moon, since
Yeah.
the center of rotation is actually outside of both of them. So should we actually be calling Charon a dwarf planet, right? They're kind of an interesting pair that way. Um, and Charon really looks like a lot of the other dwarf planets out there.
Yeah.
So
Yeah, I think once you're 12% of the
yeah,
other body, I mean that's very large for a moon.
yeah.
But that whole system's always been kind of like a, hey, you thought you knew a thing.
By the way, there's more moons than you thought.
That was so
Yeah.
exciting.
I mean, with it being right on the edge of the Kuiper belt, the potential for even things to be captured after they formed, right, is just, it leads to all kinds of interesting questions and modeling and all kinds of things that have gone on, right? And the thing about Pluto that always fascinated me is it actually comes closer to the sun than Neptune at some time. So it's on a bit of an odd orbit on top of
Oh,
everything else.
absolutely. I remember my first astronomy book was about the planets, and it was published in the early 80s. I got it through Scholastic. And it was like, yeah, right now Pluto is closer than Neptune, but that's going to change in, I think it was 1998. No, that felt so far away from me. And then I was, studying astronomy at that point. And it could be like, hey, up until just recently, this was the order, and now they've swapped.
Yeah, I mean, the outer solar system, it's like you said, we're still discovering so much. I mean, people think, oh, the solar system's set and we know. And it's like, nope, every few years, and especially as the technology gets better, we have another mission, something else pops up. It's just, I think what was really reminds us is like, even our own solar system is not that well known. Yes, we know the big planets, we know the big stuff, but the farther out you get, the less we know and the more we keep finding, right?
Absolutely. And we're just going to keep finding moons around Saturn, apparently, because I stopped paying attention. And next thing I knew, it was over 200. Like, wait, what? When
Oh
did
yeah,
this
yeah, they
happen?
add a lot very regularly. So it's quite it's quite something. That's like I said, I teach the one solar system course, and every year before I start the Jupiter and Saturn lectures, I'm like, okay, what was the last count?
What's the
Um,
tally? Let's look that up.
yeah, let's look that up. How many are we up to now? And it's like sometimes by the time I even put in the lecture, like, last article I saw was this, but this could have changed in the last month. So,
Could have changed in the
yeah.
last 5 hours.
Yeah. Like what have they found now? It's quite a swarm.
Yeah,
But even around Earth, they keep finding near Earth objects. It's just I think what this discovery really reminds us of is like we're always finding new things, right? Um
what's the quote? Space is big, unbelievably big. Think of the biggest thing you could think of. It's bigger than that. Something along those lines.
and it's just there's so much to discover out there.
Yeah.
Um so I'm gonna move so the next thing was that's of course happened recently, and it's kind of history, kind of current events, is of course the solstice was this past weekend. Um and sometimes as astronomers we don't pay as much attention to it, just because it's lovely to observe and everything, and then okay, it's over and it's done with. But if we stop and think about it, it's actually sort of one of those interesting phenomenon that we've literally been observing for thousands of years. We forget in our modern timekeeping sort of world that it used to be that astronomy was a very practical science because it's how you told time. Like you followed the patterns of the sun, and the stars to tell you when in the year you were. And that's really how people told time. They really thought of the solstice as a particular time of year, especially when you're an agrarian society that needs to sort of know, like, when am I supposed to plant? When am I supposed to harvest? Because, of course, the weather is not always a great indicator of where exactly you are. So it's been a very key time marker in a lot of civilizations. Now, as you get closer to the equator, it doesn't have quite as much importance because the closer you are to the equator, the less change of day length there is. So they still note it, but it's not as significant. But of course, here in the northern hemisphere, or when you go farther into the southern hemisphere, when you hit the solstice, of course, that is the day where you have the longest time between sunrise and sunset. And the further north you go, the more extreme it gets. So we tend to really notice it, and a lot of northern cultures really noticed it. Um, and that's where actually even the word solstice comes from. It's derived from the original Latin sol, which of course is sun, and then sistere, which means to stand still, because literally at the solstice, the sun seems to kind of stand still. Now we think about ancient cultures, when we talk about them, we think, oh, well, they mark the exact solstice. It Most of them weren't quite that precise. There is about a 2-week period around the solstice where the sun seems to sort of stand still in the sky. Like it doesn't change very much where it rises, what its highest point, what its sunset point is. And this is what they were really tagging, not necessarily the specific day or the specific sunrise, but this sort of roughly, few day, maybe up to 2-week period where the sun really seems to stand still, because we think about, days getting longer, days getting shorter, but around the solstice, it stays pretty static for changes only very small amounts for several days. And this is really what they were tagging. So when you look at something like Stonehenge is probably by far the most famous, and the modern day Druids and people go to Stonehenge for, the summer solstice, and they watch it rise. But realistically, you could probably go for a couple of days on either side and see pretty much the same thing. So we can track it very specifically astronomically now. But historically, it's been a very important sort of point in the year. What is the solstice? Actually, we tend to think about it as longest daylight, but realistically, what it is, it's when the Earth is tilted the most. And this is actually where our tropic lines come from, because if you think of that sort of tropic line on Earth, it's at 23.5 degrees, and that's how far the Earth is tilted. So really what the solstice is when the sun kind of hits and stands on that tropic line, when it sort of hits that sort of most northern extent or most southern extent, which is actually what creates our tropic lines when we look at Earth. So it has a whole bunch of sort of associations this way. The other thing, of course, is if you watch it, it varies by about a day or so. Sometimes it's the 20th, sometimes the 21st, moves around a little. This comes about for a couple of reasons. One, of course, we've got leap years. So the year is actually like a year, like a 365 and a little bit of a day. So that's going to shift it. And Earth's orbit is not, of course, exactly round. And you have subtle things like precession and nutation and things going on. So it varies by about, a day or so, sometimes the 21st, sometimes the 20th. So it shifts around a little. And again, going back historically in the Old English sort of traditions, they called this midsummer. It wasn't really the middle of summer. It is not even the hottest time of year, but it is the point of the solstice. And this idea of midsummer wasn't necessarily a specific day. It was kind of this time period, which relates to what I'm saying about the ancient observations weren't that exact. So they knew around this day for a few days on either side, you had the sun sort of standing still. So around that sort of, June 21st, June 24th, June, that kind of few days, that was their sort of midsummer. And the exact same thing happens actually in the winter, shortest day, but that's also why you have midwinter and you have sort of Christmas slapped in there. And it's not, oh, it's the 25th, they missed the solstice. No, they didn't recognize the solstice quite so specifically as we do now. So they looked at it a little bit different historically. Astronomically, it's the start of summer, although from a meteorological perspective, they usually talk more about the beginning of June being the start of summer. But before you had like accurate clocks and accurate timekeeping, it was really the way you could track where you were in the year. Okay, we've hit the solstice. We've got, 4 or 5 days of the sun is at its highest. and then it's going to start to shift, and I know where I am in the year if I need to plant my crops or all those kinds of things. So it was a very important time marker for many, many societies, and a fairly easy one to track. If you watched even for a few years, you could figure it out. So
Yeah, stick a few sticks here and there, check them. And I think you're right. You can see different, like, large scale building projects all around the world having to do with solstices and equinoxes. Like, I don't know, nearly 20 years ago, I went to Mexico and visited Tulum, which was really cool. And we learned about how, certain windows are lined up so that the sun will shine through them on the morning of the solstice, which is really cool, that not only with observations made, but like big projects were put forth to like track these things. I think it very much shows how important these time markers were.
yeah, I mean, Stonehenge is probably by far the best known ones, but most monuments around the world, if you really study them, whether it's the Maya or the Aztec in Central America, whether it's the medicine wheels across North America, like all kinds of ones, they mark the solstice. Now, the closer you get to the equator, you find the cultures put a little less emphasis on it, just because the day length doesn't change as drastically. Like they could still mark it because you could see the sun had reached its sort of farthest northern or farthest southern point. But the closer you get to the equator, the less variation there is. So it's less important to them. But the farther away from the equator you go, you see a lot more of this marking. So it's quite interesting to see how, even at different points on the earth, culturally, how a lot of them, marked it at different times. So it's kind of, but most of the advanced ones did mark the solstices, even if it wasn't as big a time thing as say it was, like in England where you've got Stonehenge, or Ireland where you've got that Newgrange tomb, or a lot of tombs actually. Not so much the pyramids in Egypt. They do have some alignments, but they're not so much solar. Not a lot of them.
Yeah, more stellar from my
They're
understanding.
more they're more stellar. They're more stellar.
When certain constellations, I think Sirius, when
Sirius is the
Sirius
very
is
important one.
visible, yeah,
Yeah.
that's the really important one for timing crops.
Because at the point where they were sort of at the height of their civilization, Sirius would rise, have its helical rising, so it sort of first reappear in the night sky around the same time the Nile River flooded. So that's why it became so important to their particular culture.
Yeah.
But yeah, it's kind of fascinating. Like the solstice is the really obvious one, but there's so many of these different alignments that the different cultures followed depending on where they were in the world. And nowadays we kind of like, oh, it's like a brief thing, and a few people go to Stonehenge or various other monuments and kind of, okay, we're gonna watch the sunrise and everything, and then we all, skittle off back home. But you sort of forget what the significance in a very practical way was, in our light polluted world.
Sigh.
And electric timepieces, we have forgotten, I think, what a resource the sky was. Yeah, it's one of my pet things, and I've taught the history of astronomy course at York a number of times. So, I try and plug it when I can. But yeah, it's just I guess I'm fascinated by sort of how timekeeping really originated with astronomy, and that's why astronomy was originally a branch of mathematics, because it was used for a lot of these very practical calculations. So.
Yes, there are many rabbit holes to go down in that particular topic.
So, well, so it looks like we're almost at the midpoint of our show. So just a reminder, you are listening to York Universe, the space and astronomy podcast from York University. We are broadcasting live from the Allan Carswell Observatory at York's Keele campus in Toronto, Ontario, Canada. I don't know if we have quite gone to no, we haven't quite, we don't. We haven't quite gone to live viewing yet, but hopefully it will be dark enough before the end of the podcast. Again, it is the sort of very late sunsets right now because we are close to the solstice. So hopefully we'll get in a couple of live images towards the end of the podcast. But again, if you're sort of listening to us later, you can go to the website at yorku.ca/science/observatory to join the chats that we have going on along with our live viewing every Monday night. Again, tonight you're listening to myself, Mary Helen Armour, and Julie Tomei. A couple of other quick announcements. Our observatory is having its second annual Astro Fair. It will be on August 29th. The tickets will be $30 for admission. This includes a full astronomy day planned by the observatory and its partners to bring you booths, activities, telescopes, and the Astronomy in Action Planetarium, which is a really cool activity where you can go in and they actually have like this inflated planetarium and they give you a really amazing tour of the sky. So even if the weather is really crappy that day, we can still do that one. Visitors will be able to do our solar system walk. We will have sundials available. There'll be a number of science-based activities and games, all for the one ticket. This is sort of an all ages event, so it's a great sort of family event if you have kids that are interested in science and stuff. For those of you who have come to the atrium tours in past years, we have to apologize, but they are doing significant construction to the parking garage this year. So for safety reasons, we can't really have people up there. So they are on pause for now. But if you go to our webpage, you will see that we are organizing what we call some pop-up observing throughout sort of the next month or so. And they'll have updates on that on our socials. What the pop-ups are is we have 1 or 2 portable telescopes where we will, on clear nights, usually Wednesdays, go to sort of various locations on campus and just be available for people to look through the telescopes at what's in the night sky. And our great observatory staff will be able to sort of answer your astronomy questions at that point.
Okay. So fun.
So fun. and the pop-ups are kind of fun because they're a little bit more informal, right? It's like, okay, what can we see in the sky on that night? And people can kind of talk and, you know, even just come by for 10-15 minutes, right?
Yeah, and like I imagine you get a lot of people who had no idea what was happening, or like, hey,
it's another way.
What you doing here?
We're gonna set up. People walking through the campus, like, where are you coming from? It's like, oh, York has an observatory. I didn't know York had an observatory. And I had $1 for every time I've heard that.
There would be so much operating budget for the observatory
for years. I didn't know we had an observatory. Or other faculty, well, I know there's an observatory, but I've never been there. I guess I really should go one day. Yeah, public tours every Wednesday night. Really? Yeah, we've had for like decades. Oh, I didn't know that.
Yeah. The number of people who came through when I was working at the observatory who were like, it's my last year, so I figured it was time. You had 4 years. You could have come back again and again.
So now we're going to move on to, I guess, sort of more recent news. So I think you had some information on LISA.
Yes. Okay. So LISA, the reason this caught my attention was because like back in 2001, I did a presentation on LISA for one of my astronomy courses. But anyways, the mass of asteroids is really hard to measure, but also is really important in determining what would happen if they became an impactor, i.e. if they're a near Earth asteroid that might be at the same place the Earth is going to be at some point, or when thinking about asteroid mining, like how many potentially available resources might be in this asteroid. Masses are typically measured using optical imaging and estimates of density from spectral profiles. And a new paper recently published proposes using LISA, the Laser Interferometer Space Antenna mission, to get data for mass calculations for nearby asteroids with all using the existing hardware. So it's kind of like a byproduct of the mission that is planned. So currently, our mass estimates can be done with up to 10% uncertainty. And this is for less than 35% of near Earth asteroids. So big uncertainty on few asteroids. The most accurate measurements are possible when asteroids are part of binary systems, because we just have more data there to do calculations based on orbital dynamics. Sometimes asteroids become temporarily gravitationally bound to larger objects. I think it was like maybe a year or so ago, there was an asteroid that became a temporary moon of Earth. We had 2 moons for a couple of weeks there. So that sort of thing. And then those data can be used in calculations, again, with orbital dynamics. The most accurate way to measure the mass is to send a probe. But there are 41,000 near Earth asteroids known. And so that would be way, way too expensive. LISA is designed as a gravitational wave detector and is expected to launch in July of 2035. It will consist of 3 separate spacecraft in a triangular formation and like aligned very precisely using lasers. And its mission is to measure ripples in space-time caused by events like merging black holes. Think LIGO, but in space. Each spacecraft has a falling test mass and instrumentation to measure any changes to these masses on the picometer level. NEAs coming close to them, specifically in this so-called minimal orbital intersection distance, would tug on these masses in ways that are measurable by the instruments. This was actually initially seen as a bug in the system, like, oh, we're going to have to account for these things. But it's now been shown that it could be a feature. Simulations have shown that should an asteroid pass close enough, LISA could be used to determine its mass with a maximum uncertainty of 20%, which doesn't sound that great, but it's much better than what we have for most asteroids out there. This, of course, depends on the serendipity of asteroids coming in range. And the estimate for the 10-year lifespan of the LISA mission would be to calculate the mass for about 3 asteroids. Again, does not sound like much, but it's also estimated that we only know about 38% of the NEAs larger than 140 meters in diameter. So there's also the possibility of discovering asteroids as they wander into the proximity of LISA and are measured.
So yeah, I remember following the LIGO project many years ago when they were first doing it on Earth, and wrote a project as an undergraduate about it. So I'm really putting myself in context here. May not be a good thing, but it's like you said, it'd be fascinating if they could actually do this. Yeah, maybe it's only 3 asteroids, but that's 3 more than we know now. And the thing is, if you get accurate ones for these ones and they come near anything else, you can refine it further, right? And that's their estimate of 3. It could be more.
Could be
none, but it could be more. And it's like, if you're out there anyways and you've got the data, why wouldn't you use it? I mean, partly they want to keep, I'm sure, the array away from too many NEOs because you don't want one of them to run into it, admittedly. But it would be sort of fascinating. And as someone who looks at sort of impact craters, mass is a big problem if you don't know how much it is, because the more mass it has, the bigger the hole it will make if it hits you.
Yep.
And if you ever get to the point where we have to deflect one of these things, you need at least a decent estimate of its mass. So you know exactly how much you're trying to deflect.
Yeah.
So
It's an interesting side quest. I like it.
yeah. So it's like I said, I kind of knew about Lisa. I didn't hadn't followed it in that much detail, but any mission that has multiple uses is always good. And I think it makes it easier to sell to people if you say, well, look, we can get the mass of these asteroids that might be threatening Earth. And then they go, okay, yeah, I understand why we need to do that.
Yeah. Here's some money.
Yeah, it's easier to get money out of like governments. You can say, well, look, it's part of our space watch. We'll add this. It's sort of like it's one of the things the mission can do. You don't have to go into too much detail that it may only be a few. But yeah, it's like it the more you can get out of a mission, the more bang you get for your buck. Right?
Mm-hmm. And I mean, even if it does end up being only 3 asteroids, we sent a whole mission to 1 asteroid.
Yeah. Yeah. So to put it in perspective.
Granted, very cool mission.
Yeah. So, well, yeah, because we've sent them to, well, I guess some of them have also been to comets, because of course there was the Rosetta mission.
Yeah. Yeah.
And there are others out there, one I'm going to talk about a little bit later.
Yeah.
But it's like I said, when we talk about mass, of course, the other one we want to know the mass of is comets, for much the same reason as asteroids. And I guess potentially Lisa, if it picked up a comet coming close enough, could figure out the mass of those ones as well.
Yeah, that would be pretty
get a more
cool
detailed
too.
one. And there are always unknown comets coming into the inner solar system, so I don't know if they've calculated the possibility of a comet coming close enough, but that's another sort of one they could look at out there.
Oh, for sure.
Yeah, because of course the next sort of little article I was looking at is, of course, looking at the James Webb Telescope, detecting methane in the recent Atlas comet. And what's interesting about detecting methane is methane actually breaks apart fairly easily, especially when it's exposed to UV out in space. So if there was methane detected, it had to have probably been frozen under the surface and then melted out during its progress in, because methane does degrade fairly easily. So it must have frozen methane on it. The other really sort of cool thing about it is we know in our own solar system what abundances are for various objects. Like there tend to be certain ratios. And yet, when we look at the ratio of methane to water on this Atlas one, the amount of methane is much higher than you would typically find in an object in our own solar system. It was surprisingly high, which also, again, tells us that the chemistry outside of our own solar system, the basic laws of chemistry apply, but the kind of chemicals and the details of the chemicals you might find could be very, very different, which has all kinds of interesting implications for, life arising on other planets, and that kind of thing. And the interesting thing too is, like, what is the source of the methane originally? Because methane is broken up so easily, it raises some other questions about how did you end up with this frozen methane on this object that's obviously been traveling for some time. Because the thing that always comes out when you start talking about methane is, yes, you can produce it through straight chemical processes, and it's not an uncommon molecule in the outer solar system, but it's an organic chemical, so there's always the possibility that it could be produced by something biological. Now that's probably a little way out there with a comet, but it sort of opens up all kinds of interesting possibilities, right? It's just sort of one more little piece of the puzzle, right? And Webb actually was cool because it got some pretty detailed compositional information on it. It was also unusually rich in carbon dioxide, again, releasing a lot more carbon dioxide relative to water compared to comets in our own solar system. In our own solar system, water tends to very much dominate, but it seems like with Atlas, the levels of methane and carbon dioxide relative to water were also quite high. So, what kind of different chemistry created an object with these sort of different balances on them? Because as a comet goes around the sun, methane and carbon dioxide will melt off quicker than the water. So that's probably partly some of the reasons that anything comes into our inner solar system gets more deficient in those quickly. But yeah, it's kind of quite interesting. So it's kind of interesting to see like exactly what happened with Atlas, because its whole sort of compositional thing was notably different compared to our own solar system comet. And this is just one of another sort of, fascinating things that Webb was able to observe. Again, going back to that idea with the Lisa, that it's often sort of some of these sidebars that these missions pick up that lead to some really interesting results. So yeah, there's some really cool results. And Atlas has been gone for a little while, but we're still getting this data that's taken a while to process. And so we're still getting sort of new results out of it, because it just takes time to go through all the data that these kind of missions produce.
Yeah, absolutely. And Webb, I mean, it's like every other day there's some cool Webb story that comes
I know.
out.
So I'm like, okay,
Great
what's the Webb
telescope.
story of the week? You could do a whole podcast on that alone. So
Yes, we could.
you might get a little tedious for people. I was like, come on, let's move on to something else.
Well, we do like to offer, variety. Here it's the spice of life.
So I think you moved on to a different telescope for
A
the next
different
one.
telescope, yes. One that is maybe not as new or shiny as Webb, but definitely one that has really been a workhorse, I would say. We're looking at the Hubble Space Telescope and specifically deep field imaging. So the first Hubble Deep Field was taken in 1995. It was the first this first image was a test to see what would happen if you observed a piece of sky that looked empty. So the wide field and planetary camera 2, which had recently been repaired, was pointed at a patch of sky in Ursa Major, about 1/13 the size of the full moon. And sidebar, we are looking at the moon right now through the big telescope. Huzzah! So 342 exposures were taken, giving an exposure time of over 100 hours. And the results were breathtaking. I mean, it's a beautiful image, but also there are over 3,000 large galaxies at different points of their evolutions in this image, which accounts for 0.0000035% of the night sky. So I've used this image a lot just to say, hey, hold out your thumb at arm's length. That patch of sky was the size of your thumbnail. And there were over 3,000 galaxies. How many times can you put your thumb in every direction? Like, just think about how vast the universe is. Because it was so awesome, many subsequent deep field images have been produced. They did the Hubble Deep Field South in 1998, which resulted in a similar image. And possibly the most famous one is the Ultra Deep Field, which was released in 2004, which looked at an even smaller piece of sky. So take a grain of sand, hold it at arm's length. That's the size of sky they were looking at with this one. And they found 10,000 galaxies. And that just is a couple of deep fields. You can, one thing I did today was like, how many deep fields are there? And there's a list that you can find of not only Hubble deep field images, but other telescopes have done the same thing. The latest release of a Hubble Deep Field was just a little while ago on June 12th, featuring a galaxy cluster named Max 0329-0211, because we are really good at naming things. And it is named after the Massive Cluster Survey, which found that cluster. And it contains more than 1,700 galaxies in and around that cluster. Some of them are, quote, feeding on the edges, leaving like a visible aftermath seen in this like ghost light glowing between galaxies. And this is thought to be what remains of dwarf galaxies that were torn apart by larger galaxies. And some are background galaxies that are being lensed by the cluster. So they're all like stretched out, but there's like big, like spiral, elliptical, like all like the really big types of galaxies, and seen from like different angles. Some are like face on, some are edge on, different angles. Is a really cool image. I'll drop a link in the chat. And this cluster was of particular interest because of its brightness in X-rays, and the Hubble observations were done in visible and IR light.
Yeah. I mean, Hubble has just done so much for sort of the whole field of studying galaxies, because it's been able to find so many. And most of them would not be visible from Earth because they're so far away and you have to take such long exposures. It just wouldn't be possible with an Earth-based telescope. So it's like I said, the number of galaxies it's found and allowed people to really get like this huge, I guess, pool of objects to study is just, it's a little bit mind-blowing with the sheer amount of data. I mean, that's things sometimes I think what people sort of kind of forget is when you look at something like Hubble, like how much data it collects. I mean, when you think, okay, well, look one grain of sand, like how many grain of sands would it take to cover the entire sky, and therefore how many galaxies could be out there? Now, obviously they aren't all evenly spread. There is different things in different directions. But if you think about it, and all the weird and wonderful things it has found, because there's so many different ways in which they interact. It's like you said, the galactic cannibalism, as they sometimes refer to it, which I always found that was a crazy term, but it sounds good.
Om nom nom.
Yeah, and it's like I said, it just, I mean, one of the reasons it was named Hubble, because they were hoping to better calibrate the Hubble constant. I don't know if that's gone quite how they expected it to. But yeah, it's from a galactic standpoint of sort of galactic sciences, Hubble was really, it just advanced everything.
Yeah.
So much, like the sheer number of observations it was able to take of just everything. I don't know how well it's still working. I know there was talk of possibly doing another repair mission to Hubble.
Really?
Seen anything more about that? I know there was some debate, or if they were just going to say no at some point, we're just going to let it go and we'll focus on the Roman telescope instead.
Yeah. Yeah. I mean, it's been going a long time.
Oh yeah.
Right? Like, I was in elementary school when it was launched.
Well, it wasn't quite in elementary school anymore, but yeah, I mean, I actually remember them like talking about having to like delay the launch because of space shuttle issues, right?
Right.
Because it went up on the space shuttle. And of course, just prior to that was one of, I can't remember which one that went in the 90s. Was that Columbia? Because the Challenger was earlier than that.
Yeah,
Challenger
Columbia was 2001.
Columbia was 2001.
So
maybe
it probably was because of Challenger, because like 86 to 90
Yeah, so
it's only a
it's
few
like I said,
years.
it pushed back so many missions
Yeah,
when it did, because they didn't fly for like a few years after that.
exactly.
Um, and then it would have had to launch and go through calibrations and all kinds of stuff. And of course, lots of fun with having to give it glasses.
Yes.
It's like you just wonder how great some of these images might have been, if they hadn't had those tiny flaws. Yes, they corrected it, but was it ever as good as it should have been if the mirror had been perfect, if it didn't have those flaws in it? So, but yeah, it's like I said, I mean, it was still amazing, but what could have been if they hadn't needed like correction?
Yeah.
I mean, how much the correction affected it, I don't know, but yeah.
I just think it's amazing they were able to fix that, and it's been chugging away, giving us so much data.
I know. It's like I said, it's just probably the smartest thing they ever did was made it serviceable, because it allowed them to keep updating
Yeah.
and improve it. Because otherwise, like, you think about it, 1990s computer technology, 1990s storage capacity,
Yes.
would have been so different from what we
How
have
many
now.
bits per second can you
Yeah,
send
I
over?
know. It's like I said, it would have been the scope of what it has sent to Earth. Yeah, if you hadn't been able to sort of update it regularly over, 10, 15. Well, when was the last service mission? It's been quite a while.
It's been a while because the last shuttle mission was in 2011.
Yeah, so it probably was not long before that. Um, but they would have done the last one. But
Yeah.
the fact that they were able to update it for like 10 or 15 years after launching it, it's probably what kept it going for quite so
Oh,
long.
absolutely.
So, uh, so we have one more mission I wanted to touch on.
Yes.
And this is going back to asteroids again, and missions to asteroids. And one I have been following is NASA's Lucy mission. And this was actually, strangely enough, named after a fossil that was found of an early
Ah,
human species. That's where the
yes.
name Lucy comes from. It's not named after somebody's wife or girlfriend or dog or a Peanuts character. It's actually named after a skeleton, which I always thought was kind of funny. There's a connection. I don't remember what it was. But Lucy is was launched in 2021, so it's already been flying for a number of years. But it's doing a lot of asteroid flybys. Its next flyby isn't until sometime next year. But last year it flew by an asteroid called Donald Johansen. I'm not entirely sure where the name comes from. But it was one of the one that's chosen. Lucy was mainly going to focus on the Trojans, of course, which are a group associated with Jupiter because they sit in one of the stable Lagrange points on Jupiter's orbit. Um, but this one is in the main asteroid belt. It managed to collect a close-up image last April as it flew by, and it flew by fairly close. It was within a few hundred miles. So in space terms, that's pretty close. And what was really interesting when they analyzed the data about this Donald Johnson, most things when you think about rotation, of course, Earth rotates on its axis, so it just spins, and it's a fairly simple spinning motion. On the other hand, Donald Johnson is kind of peanut shaped, as they call it. It's got a lot of craters and ridges on its surface, and its rotation is a lot more complex. It actually has a two-axis rotation, which means it's got two directions of rotation at the same time. So it's kind of rotating around more than 2 points. So it looks really, really wobbly. You've got this weird wobbling rotation that it undergoes. And if you go to the NASA website, they've got some cool videos of showing how this thing is kind of wobbling along as it sort of goes. So it's quite an interesting thing. It's peanut shaped, so it looks like sort of two larger pieces stuck together. Whether probably not the original shape. They do think it's likely two asteroids that were collided and stuck together. They also have found some evidence there may have been water on the surface. Lucy did find iron-rich clay minerals, and these are generally only made in the presence of water. So there must have been some liquid water on the past. It could be very brief, but in order to create these kind of, clays, there has to be some kind of water exposure, which is really kind of interesting. So Donald Johnson may originally have been part of a much larger object that could have been carbon and water rich. And this is sort of one of the interesting results they have had out of this. And again, it's this finding all these sort of weird and wonderful things about different asteroids. And this isn't even Lucy's main mission. The next flyby it has is in 2027. Its targets are actually meant to be in the Trojans, but it's picked up a couple as it's gone through the asteroid belt, but its main mission doesn't start until 2027 when it actually gets to the Trojan asteroids. But already it's sending back some very interesting science.
Another side quest.
Well, a lot of these missions, if they're heading along through the asteroid belt, they see if they can sort of direct them so they come somewhat close to asteroid belts. Of course, with Galileo, you had those famous pictures of Gaspar and Ida as it flew through the asteroid belt. I mean, what people have to remember about the asteroid belt is it's not the Millennium Falcon dodging.
It is very much not.
It's more a case of it's very sparsely spread. So if you go through the asteroid belt, it's like, oh, look off in the distance, there may be an asteroid. It's still mostly empty space. It's just not quite as empty as everywhere else. You think about how big space is, right?
So for those who are wondering, I did go down the name rabbit hole while you were telling us about this. So Donald Johanson was one of the co-discoverers of the Lucy fossils. And the name Lucy was chosen because Lucy was like that fossil was so important to our discoveries or our learning around human evolution. And so we're going to be learning about
asteroid evolution.
Yeah,
evolution,
exactly.
like evolution of the solar system, asteroid evolution. So yeah,
exactly.
Like I knew the link was there somewhere. I'm like, okay, it's
kind of tenuous, honestly.
It's a bit tenuous. It's someone geeked out over it.
Yeah.
Astronomy people tend to do that.
Yeah, we do. Like that's okay. And the name Lucy was given to the fossils because the song "Lucy in the Sky with Diamonds" was kind of on repeat during the digs.
The strange reasons you get various names in astronomy. Yeah, it's like sometimes don't ask where the name comes from. You don't want to go down that rabbit hole.
Sometimes you don't. That one was fun.
No, but it's like I still remember when they had Sojourner and it was running around and they were naming like Rock's Barnacle Bill and various. That was the one that always stuck out for some reason. Barnacle Bill. But they had a whole bunch of wacky like character names. I think they called another one Scooby-Doo, if I remember.
Yeah, I think there was one called like Yogi or Yogi Bear or something.
Yeah, and yeah, so it's like okay, somebody's having fun with this. Yeah, scientists are a little odd at times.
I think we're fun.
Yeah, odd, but okay. So I think we're getting to about the end of our podcast, so we will wrap it up this evening. Thank you everybody for joining us. You have been listening to York Universe, the astronomy and astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been myself, Mary Helen Armour, and Julie Tomei. This podcast and past episodes are available wherever podcasts are distributed. You can always connect with us too on Instagram at York U Observatory. We are on PixelFed at Allan I. Carswell Observatory, or on Facebook at Allan I. Cars Web Obs. Okay. Our website again is yorku.ca/science/observatory. And we have lots of interesting content. And again, we are entirely a nonprofit. So if you are, we are always happy to receive donations, which are tax deductible, to our student operated not-for-profit observatory. So again, thanks for tuning in this evening. We wish you clear skies and a good night.
Good night.